Okay, so I'm Joerg Schmiedmayer. I'm typical Viennese Austrian. I'm at the Technical University in Vienna, but I worked all over the place. I did my education in Vienna. I worked at CERN in Geneva. I was at Harvard and MIT. I was for quite a while in Innsbruck and in Heidelberg for quite a while, and then I'm back in Vienna, and I spent lots of times also in Japan and here and many different other places. So what interests me most are fundamental questions in quantum science. So how does quantum physics determine how we see nature and how nature works? And I'm mostly interested in particles interacting systems, so not the single photon that goes through the double slit or a single atom, but I'm interested in questions of physics which have to do with complexity. So if you take many atoms together or many quantum constituents together, many spins or whatever you can think of, and let them interact with each other, and when they are in a regime that is dominated by these interactions, there the complexity of quantum mechanics comes to play. And what interests me is that how do out of these interactions of particles in between them, the world emerges, so to speak, on how we see it. And so how can you say that? We usually can, if we have a system of many particles, what we know about nature is not limited on by, at least in our experiments, it's not limited what we can measure, but it's limited by the computational complexity of the data analysis that we can do with classical computations. And this is an extremely severe limit of what we can know about your system compared to what we in principle could measure. And this leads to emergence of properties. So emergence of new descriptions. There are certain information which has to be disregarded, and also which become irrelevant because you can only process so much information about the system, and so you find a hierarchy of descriptions of increasing simplicity of a quantum mechanical system, and basically all descriptions that we have of interesting solid-state physics materials, biology materials, and all of these are this type of emergent descriptions. And what interests me is how do these things form? What can we learn about these emergent descriptions? How do they form? How do they come about? What can we do with them? Yeah. And so I do some of these experiments with ultra-cold atoms, but I also do something completely different, which is experiments with spins in superconducting circuits, where we also now are in a regime where we get to interacting spins and how they interact with superconducting circuits and superconducting qubits, and this may lead to a completely new way of doing quantum information processing. Okay, yes. So that's directly plays into what I said before, into this question of if you look at larger and larger systems, you basically have to zoom out. You have to coarse grain, and I'm completely convinced, and I think there is very strong experimental evidence, mainly from our own experiments, and also very strong theoretical evidence that through this way of having a microscopic physics, which is completely quantum mechanically, and then zooming out and looking at larger and larger and larger systems and finding more and more of these emergent descriptions, that if you go, far enough away, you very naturally will find, classical physics descriptions. So there is no need of some funny border between quantum mechanics and the classical world. And you can see that in experiment, and so we showed in an experiment that even in a very simple system, you see quantum mechanics, and it evolves in time, completely isolated. There's nothing coming in from the outside, and at a certain time, it looks like, for all practical purposes, it looks like a classical system. But underneath, quantum mechanics is not dead; it's completely alive, and because you can arrange the system in such a way that the quantum mechanics comes back. And so also it means that, I'm totally convinced that behind our classical world, it doesn't mean that the classical world is totally different from quantum mechanics. It's just like the classical world is a world which has so much complexity that we simply don't see the quantum world. It's completely alive in there, in the same way as classical statistical mechanics. We have a pressure and a temperature and things of a gas, and we have these quantities, which are classical quantities, but underneath there, of course, there's a microscopic physics of atoms having a velocity and hitting something and scattering and doing all these things. But that's way too complicated. That's not necessary to understand what is a temperature and what is a pressure. Yeah, and so I think that in the end we will find out that exactly the same thing happens from the classical world. And also, in some sense, quantum information told us that it's the border between quantum and classical is not between microscopic and macroscopic, but the border between quantum and classical is an operational one. It's an operation border between how good manipulations I can do in my system. If I can do it good enough, like quantum error correction thresholds, quantum information theory tells us I can keep an arbitrarily large system, arbitrarily long, quantum mechanically, yeah, with a very high overhead, which is this very high overhead is all this where these imperfections get hidden into irrelevant quantities. But it tells you that there's no quantum information theory tells you there's no border between quantum and classical. It's just a question of what can I do and what can I know. One of the devices we always use in our experiments is something called an atom chip. And it's based on the idea that if you make something small and you can fabricate it on a surface, it becomes very robust. Just compare the very first tries to make a classical computer with vacuum tubes and compare it to integrated circuits. And so the idea is that can you make them, put the manipulation, or most of the things you need for manipulation of atoms or ions or whatsoever, on a surface and fabricate it. And then if you did your calculation right, you have a device which performs what you want to do. And it's also very, very robust. And so that's the advantage of the chip, that you have something designed, what you want to do for your experiment, and you put it there, and then you have a very robust experimental device. And we started this for neutral atoms, but it was by now people use it in ion traps quantum computers. People use it for slowing molecules, and so there's all these different types of parts. And the question is, of course, will it help you to do experiments? In some sense, many of the experiments we did would have been very difficult to do without this device, because it made it possible to repeat experiments many, many times in exactly the same way and study statistical physics in that way. And ion traps ion trap quantum computers are basically based on using microfabricated, nanofabricated devices like atom chips for manipulating the ions. That's called ion chips and something. forming. So I think that's a very general way of doing it, and there's one thing, of course, when we first thought about these atom chips, we thought, we can build beautiful interferometers, we can build very precise measurement devices. It turns out that this is difficult because atoms interact. And because of these atoms interacting, there's a big complexity in this whole measurement device. And especially any interferometer is based on beam splitters and recombiners, which are prone to quantum noise. Now, in an interacting system, this quantum noise is paired with energy noise because of the different interactions. And that prevents you, this is a very, very big problem for precision measurements. So on one sense, the experiments we then did and all the science we did was looking at the physics of these interacting systems. And it's extremely rich, but it was not possible to do precision measurements as you would simply state like that. In fact, we once showed in an even if you do, make entanglement and put squeezing on there, you only come to a specific, your measurement, accuracy becomes only a specific fraction of this interaction energy. And so it is all it's a difficult question if you want to do something like gravitational wave detection or other things. It doesn't mean that it's not possible, but it's not the straightforward thing that we know from optical interferometry. You cannot put it directly on there because you have an interacting quantum system. This said, I think there are beautiful ways you can do if you, for example, work with single ions on a chip, and you can make very, very precise clocks, which you could use for that. And the other part is that you have this interacting system that allows you to make very precise measurements like local magnetic field measurements and other things, which could be used for material science properties. And so we tried this for some. We even have a patent for 20 years ago on that, but it never turned out to be. It's a complicated system because it's an cold atom system, and it has a huge overhead to do it. But something like measurement of electron transport in solids or things like this, you could think of that it could be a device which you can use. And there is also people in Stanford that are trying to do that, for example. Yeah. I think the biggest impact it will have is on ion trap quantum computation. It will allow you to manipulate large samples of ions and connect them together with photons or with just shuttled ions. This will be a big part, and because you can, on the chip itself, you can then in principle integrate many other things, like all the electronics you need for the manipulation. You can integrate all the photonics you need for detection and something like that. But it's an enormous technological overhead, and for the moment, I see only the ion trap quantum computation as an incentive to do that. Because yes, you can go and do it, but it's a very, very high technological overhead, and you had to have something which could really bring a breakthrough. And I think ion traps is one of those parts, and you could maybe think of having ion traps. You're having microscopic atomic clocks or ions as sensors. For neutral atoms, I see that this magnetic field measurement might be interesting for surface physics or something, but I don't see any. There is still a lot of research has to be done, and system with large things. It will be used for fundamental research. I'm sure that there will be lots of fundamental research, but something that where you can go and say, go into a supermarket and buy an atom chip. I think that will not happen in the next 5 years or 10 years. But I could be wrong, but I don't think so. Okay, so I first think is that China made an amazing step forward in doing quantum science, and they have fantastic output. They do fantastic science, and it's always a joy to come here and discuss with people and do that. Advantages, I think one advantage definitely is that there are a lot of resources going to that part. Compared to my own country, Austria. Of course, Austria is much smaller, but I've seen here startup companies who have a budget per year, which is more than the whole Austrian government and the European Union invested in Austria in the last 30 years in quantum science in Austria. And many of the things, there are 2 Nobel Prizes that came out in Austria, and there are people like Peter Zoller and others who really did, really shaped quantum information science very significantly. But the thing is that so really making technological advances in something, you need to have very large investments, and I think that there China has an advantage. China has an advantage that has a huge reservoir of scientists and engineers to do that. Very clever scientists and engineers, and very clever way also of all the different aspects. You're going to need AI, you're going to need electrical engineering, you need mechanical engineering, you need all these things to put together to really develop the technology. I think that's a big advantage, and also that it's very quick to build infrastructure here, compared to somewhere else where it probably you decide I want to build a clean room, and the clean room is operational even before in another country. You would have to fill out all the forms to hand in for the application, that you're allowed to do that. And so this is a huge advantage in some sense to do that.